Now we are in part B of problem 4.3. If you didn't watch the previous video, then just note that I actually made a typo in my first video. So this is a minus infinity here. So x has a lighter tail than y if log of the density of x minus log of the density of y tends to minus infinity as x tends to infinity. So what we're going to do in part B is we will compare the tail of the gamma distribution against the tail of the Weibull distribution. The funny thing here is that if you take a look at these two densities, you kind of notice that they really look very much alike. So probably the only difference is that in the Weibull distribution, you take the bth power of x. But apart from that, they kind of remind you of each other, which lets us throw caution to the winds a little bit, because then this might mean that which one has the heavier tail will depend strongly on the values of the parameters. So now let's just write down the assumptions that alpha and beta and b and a, they're all assumed to be positive. And let us just try and write down the ratio between the densities. So as before, we let h of x denote the ratio between the densities, and the way we compare them this time is that we let the gamma distribution be on top, and we let the Weibull distribution's density be in the bottom. So if log of this expression tends to infinity, then the gamma distribution is the heavier tail. And if log of this expression tends to minus infinity, then the Weibull distribution has the heavier tail. So this ratio of densities is proportional to, so here we just remove the constants that have nothing to do with x. So this is proportional to x to the alpha minus 1 multiplied by e to the minus beta x divided by x to the b minus 1 multiplied by e to the minus x divided by a to the b. So what is then the limit of this ratio for x tending to infinity? As before, since we have exponential expressions, we are interested in taking the logarithm of this ratio instead of just looking at the limit of the ratio. So I will take the logarithm of h of x, and as noted before, there is a constant that should be here if we needed an equality sign. So log of that constant will just be some constant k that we don't know that much about, but we don't care about anyways because it doesn't depend on x. And then I have plus. So log of this entire expression is first and foremost log of x to the alpha minus 1, which is alpha minus 1 multiplied by log of x. And then plus log of this exponential expression, which is just minus beta x, and then minus b minus 1 log x, and then minus minus, which is plus, x divided by a to the b. And we can shorten this expression a little bit because I can put these two terms together. So then I will have alpha minus b minus 1 plus 1 log x, then minus beta x plus x divided by a to the b. So the thing here is, well, log x grows slower than x to any positive power. So the dominating terms here are beta x and x to the b. Now, what we have here with the beta x is x to the first power, right? So which of these two terms will dominate? Well, it kind of depends on the value of b. So we have to split it into two cases. So if b is greater than 1, then the term x divided by a to the b will dominate. It will be the bigger term when x tends to infinity, right? Will dominate. And then log h of x will have this term tending to infinity dominate the entire expression when we let x tend to infinity. So in that case, log of h of x will tend to infinity as x tends to infinity. Hence, in the case that b is greater than 1, this limit is infinity, which means that the distribution in the numerator has the heaviest tail, so hence gamma distribution has the heaviest tail. However, if b is smaller than 1, so I have if b is greater than 1, but however I also have if b is strictly smaller than 1, then this term will not grow as quickly as this term does when x increases. So if b is strictly smaller than 1, then minus beta x is the dominating term. And beta x grows towards infinity, so minus beta x will go towards minus infinity. So is the dominating term. Hence, then in this case, log of h of x will tend towards minus infinity as x tends towards infinity. And then we have the opposite case where the Weibull distribution will be the one with the heaviest tail. So the thing we kind of look at first is b greater than 1 or is b smaller than 1? But however, we also have the third case, which is what happens if b is equal to 1. So if b is equal to 1, then what happens is, then I have x over a minus beta x. Because and then I can see that I can put these two terms together, right? So if b is equal to 1, then the logarithm of the ratio of densities will be equal to k plus alpha minus b log x minus, or just plus, 1 over a minus beta x. And that is also a very interesting situation because here, this is the dominating term. So this will be the dominating term since x grows quicker when x goes to infinity than log x does. So this will be the dominating term. And depending on which sign 1 over a minus beta has, then this will go either towards minus infinity or infinity in the limit. So again, we have to split this up into, oh my god, two cases. So if 1 over a minus beta is positive, so if 1 over a is greater than beta, then log of h of x will tend towards infinity, because then this term will be positive, and then when x tends towards infinity, this term will tend toward infinity and eat up all the other terms. So then log of h of x will tend towards infinity as x goes towards infinity. And, well, then again, gamma has the heaviest tail. So I'll just write gamma heaviest. However, if 1 over a is strictly smaller than beta, then this will have a minus sign, right? And then that term will tend towards minus infinity, leading to log of h of x tending towards minus infinity, as x going towards infinity. And then the Weibull distribution will be the heaviest. And recall that this is the case where b is equal 1. So actually I could have also written the 1 in here. I just was too lazy to do that. But this is the case where b is equal to 1. So if b is anything other than 1, we don't need to think about the difference between 1 over a and beta. Then we just know if b is greater than 1, we have gamma is the heavier one, and if b is smaller than 1, then Weibull is the heavier one. But if b is equal to 1, then we need to split into more cases. So here we have the case where we have 1 over a greater than beta, and the case where 1 over a is smaller than beta. However, we have not considered the case where 1 over a is equal to beta. So we also have to take into consideration that case. So if b is equal to 1 and 1 over a is equal to beta, then how does this density look? How does this log of ratio of densities look? Then log of h of x is equal to k plus alpha minus b, where b is just 1, so alpha minus 1 log x, right? Because this thing will just be equal to 0. In this case, it is quite clear that when x tends towards infinity, we have again two cases. Depending on the value of alpha, this will either go to infinity or minus infinity. So we have that if alpha is greater than 1, then log of the ratio of densities tends towards infinity. Hence, the gamma distribution will be the heaviest one. Heaviest. However, if alpha is strictly less than 1, then this logarithm of the ratio of densities tends towards minus infinity, and the Weibull distribution will have the heaviest tail. And what about the case then where alpha is equal to 1, you might ask? So the case where b is 1, 1 over a is equal to beta, and alpha is equal to 1, well then this just completely cancels out, right? So in that case, what we actually notice by looking at the densities of the gamma distribution and the Weibull distribution is that if beta is equal to 1 over a and b is equal to 1 and alpha is equal to 1, then what we actually get is then the distributions are equal. Then the distributions are actually just the same. So you can just check that by taking a look. So then the distributions are equal. And not surprisingly so, because they already remind of each other a lot. So that was the exasperatingly long solution of problem 4.3b. For the next comparison of tails, watch the next video.